Hello, and welcome to what will probably be the last demonstration of SystemZero. In this video, I want to demonstrate a number of things that I've achieved over this week. So let's start off by compiling the OS. And this is on my desktop, so it shouldn't take long at all. And yeah, there it is. Let's just write the license. And the first thing you'll notice is the boot is, it's as fast as usual, so it's pretty slow for the size of the operating system, I must say. This operating system is not even like 100 kilobytes in size. And yeah, it takes a couple seconds to boot. What's with that? So you can see calculating system drive size and finding free data block. This is actually the installation process for SystemZero. So it installs itself onto the drive once, it saves all the data about the drive and the file system and where the free block is and whatever. So actually, because it finds a free block on installation, whenever we create a new file, it takes barely any time. Unlike previous demonstrations where it took, say, if it takes 37 ticks now, by the way I added the benchmark thing here, it took, say, 2000 ticks in previous iterations of SystemZero. And this finding free data block and scanning the disk for what size it is, it does not repeat on next boot. So you can see next boot is pretty much instant. And the message is gone. And if we list and touch a file, it's just as fast. And that's pretty sick. Now, the next thing, so this is actually like what I want to show. The actual visible and part that you can experience. You may have noticed there's a 0 in front of the benchmark. So what's with the 0? Well, that's actually the return status of every command that I run. And the return status is just information in the form of a single integer that tells the shell about how well or how badly the program had ran. So all of these programs have ended in a success, I would say. But if I go to, say, okay, if I do drives, you can see all 4 exist, but if we go to drive 4, so there's 0 index, so drive 3 is the last one, and 4 doesn't exist. If you go to 4, it returns a 1. And generally, anything above a 0 means trouble. So, in this case, 0 is good, 1 is error in the program, and if it's a non-existent file altogether, it returns a 2. So now, why did I implement this? What's the point? The point is chain. Now, chain is a very interesting, very cool program. It's essentially an interpreter for a single-line programming language that I have developed. And yeah, this is actually pretty sick. So if we do chain, as the name suggests, initially this was a program that was supposed to chain together commands. So say we want to go to drive 1, and by the way, the syntax for this is it consists of statements. And the statement is started with a $, and then we just have the statement, and then it ends, or if we want to put another statement after it, we put a $sign in front of it, like this. So drive 1, and then we do format. So format it, so go to drive 1, then format it, then go back to drive 0. Let's try this. It's formatting IDE 1, and it went back to IDE 0. So that's sick. And now, another utilization of chain is printing strings. So this isn't like, you're not supposed to do this on its own, really, but you can. So you could do hello world like this. To print a string, you just do a statement and quotes, and inside the quotes is the string, and it'll be printed out to the terminal like this. Now we can actually write programs because this has conditionals and has jumps. So how do conditionals actually work in this weird programming language? So first we need a statement that will return like variable output. So say list always returns 0 because really there can't be an error with listing all the files in the disk. So we can do chain, and then let's do drive, and then drive 4. So the drive 4 doesn't exist, so this will return a 1. How do we make use of the 1? So we put the 2 tildes like this. So instead of quotes now, it's 2 tildes. And the tildes symbolize a conditional. In the conditional, we first put the return status that we want to condition, or I don't know what the term is for this, but we're checking if the previous command that was ran returned a 1. So if it did, we put another number, and this number denotes the statement that we want to go to. So say statement 4. Now, currently we don't have 2 statements, so let's make the other 2. And these will both be strings that will be printed out. So this is statement 3, and let's do like 1. And the statement 4 will be a 2. Now, what this will do is it'll try to go to drive 4, this will return a 1. It'll then check if it returns a 1 here, and if it does, it will go to statement number 4. So it will skip this 1 here and go to 2 and print out 2. Let's try it. There it goes. Drive doesn't exist and 2. So that's what we expected. However, just to show you that this isn't like a setup, I'm gonna do the same thing, but this time check for a 0. And like this, and another statement like this. So now it prints a 1 and a 2. How do we make it only print a 1? Well, of course, to make something Turing complete, I'm not actually sure if this is Turing complete, but no, it's probably not. But to make something a conditional, we need conditional jumps, and we also need unconditional jumps. And we have unconditional jumps. So if we do drive 4, and this time we have 2 of these conditional statements, and I won't put in the statement it will jump to just yet. So I'll put a 0, and then I'll make another conditional statement, and I'll put a 1. And then I will make a statement which will print a string and another one, and I'll do exists and doesn't exist. Now, how do we put logic into this? Well, generally, after this one, we'll put a unconditional jump. An unconditional jump is denoted by 2 @ characters, and between the @ characters we put the statement we want to jump to. So I won't fill that in just yet. So now I think we have everything. At the end we'll just put a just an empty statement that won't do anything. And so we have drive 4. Then if it's a 0, so if the drive exists, we want to go to, so this is 2, 3, 4, 4. We want to go to 4 if it exists. And we want to go to 5 and 6 if it doesn't exist. And then here, so after it goes to exists, we don't want it to print doesn't exist straight after that, so we go to 7 here. So 7 will be this statement. And now, if the drive exists, it will print exists. If the drive doesn't exist, it will print doesn't exist. Let's test it out. It works. Doesn't exist. Let's try it with an existing drive. So just retype the command here. It's too bad that there's no up arrow to bring back the previous command, but that's fine, and I'll probably implement that soon enough. Doesn't exist, and the blank statement after. So now this is drive 3 is checking, and this will print exists. There it is, exists. So this is Chain, the SystemZero weird interpreted programming language. And it actually went to drive 3, so that's pretty cool. I guess at the end we could put the drive 0, so go to drive 0, which won't actually go to the drive, we'll just check if it exists or not. That could be an idea, but I won't do it because what's the point? Now finally I just want to do a real quick thing where edit license, and I'll just show you how fast this saves compared to the last time I showed you the text editor. So, hello world, these are some changes. Control S, boom, and saved. So for a 35 kilobytes large file, like, I think Vim doesn't save much faster than that. So that's pretty cool. Oh yeah, and I don't think I've actually shown the color command. So the color command takes in two numbers, and these are the VGA color codes. So the first one is the background, and the second number is the foreground. So 0 is black, 2 is green. So we can have a HackerMan terminal like this. List. Boom. HackerMan terminal. And we can hex edit, license, whatever. Have I shown this? I don't think I actually have shown the hex editor. But this is the hex editor. We can insert a byte. We can do like 4.1 for capital A, 4.2 for capital B, and this is in hex, by the way. 4.3 for capital C. These 20s are all spaces. We can delete them with D. We can change bytes with C. And, well, we need to actually put in a valid hex number, which is 12. Change that. Page up and page down can scroll. And W to write changes. So there it is, written the changes. And now if we view license, I have the ABC NNU and the weird character inserted when I changed the space. So that's pretty cool. That's SystemZero, my own custom Ring 0 operating system. I hope you enjoyed this demonstration, and see you in a bit.